Cosine's missing. Tangent's missing. Let's see what else. We got secant missing. And 5 cotangents missing. So I'm trying to come up with the values for those based on that given. And you must, when I answer these, you gotta give me a rationale why. Why did you say that answer? Or why would I place the answer on the board? I gotta give a justification. Guys, when I look at this, you'll have one of these on your first quiz on the trig part of the course. Be next week. In the exam next Friday is a lot of trig. Which of these 5 remaining ones would you like to find first? Based on, and tell me the rationale, tell me why, and we'll do it.
Cotangent.
I see one that's easy to find based on the given.
Sine.
Okay, here we go. I gave you cosecant. Students are saying sine. What's the relationship between these two? In fact, they are, where is cosecant? Right here it is. They are reciprocals. So I can quickly say sine must be then, if cosecant's a -4, must be quickly what? -1/4. Finished. Now if I say why on the quiz, give me a rationale, you write this identity for me. That cosecant, where was it? It is cosecant is equal to 1/sine. Now the others may require a little bit more work, but I can find the others with the help of the identities also. Guys, that's up to you. Does anyone now have in mind another of the values to find and how to find? Give me a rationale. Which of the identities would you be using? And I don't care which one you find, as long as you give me one of these to justify. Guys, anything at all to ask about? Or answer?
All right, goofed.
Because I have 1, 2, 3, 4 still missing. Cosine. Now, if you want me to find cosine, which of these over here would you use for a justification? You got to justify for me. Which of the identities would help me find cosine? Okay, got those there. Okay, so tell me more. That's what I want to hear. Now, you said, Professor, these were like definitions here. Now he says, wait now, right at the end of class, I think also, were we not writing some identities like these? But I think we added some to the list. I got this right here. He's telling me, Professor, I remember one from yesterday that said this, if I need it. Another basic trig identity. Another one, sine squared plus cosine squared. Another one is what? 1 plus, help me out, you guys, 1 plus tan squared is equal to secant squared. Do we recall that one? I think I did these probably right at the end of class. 1 plus cotangent squared. And guys, what was that equivalent to? Cosecant squared. Now someone check, are those written correctly? Were those the others that we came up with probably at the end of class? Okay, now he's telling me I can find cosine, if I wish, by using maybe this one, sine squared plus cosine squared is equal to 1, to find this. Okay, on the side here, guys, I need, in other words, let me use this green marker here, sine squared plus cosine squared is equal to 1. And if I do it, we think sine is a -1/4. I can put that in, make it substitution. Guys, we'll solve this like you would, I'll get out of your way here, like you would an equation. That's a 1/16. Move that over, subtract it, what is that? 1 subtract 1/16. I think it's 15 over 16. Make sure you see the screen. And then take the square root. Now at this point, it's plus minus. Radical 15 over 4. Is that true? At this point, it's a radical 15 over 4. But I can't accept plus and minus. That's why they give you in this additional information. So you'll find which one is it. It's going to be a positive answer at the end here or a negative answer. Okay, let's see what happens. They gave me cosecant is negative 4. Guys, cosecant is 1 over y. So as I travel through the 4 quadrants, where is 1 over y going to result in a negative to begin with? Which quadrants?
2 and 4. Oh, 3 and 4, sorry. And 2.
But at the same time, they're saying, hold on, tangent must be positive. That's y over x. So if you go through the 4 quadrants from middle school and put y over x, those coordinates, where am I guaranteed you're going to end up with a positive result? 1 and 3. And why 3? Because I think the coordinates of 3 are what? Negative and negative. If you place a negative over negative, it turns into a positive. Where do they match up here, guys? Looks like they match up in quadrant 3. So that's where my angle is located. Philip, I have no idea what size this angle is. They used to call it theta. But I now know where it is. It's in quadrant 3. If it's in quadrant 3, I know and you know the coordinates are those. Now let's go back to where I stopped here. We got cotangent to be plus minus. I've got to decide is it plus or is it cosine? Plus or minus, well guys, cosine is what, x? So it looks like if I'm in quadrant 3, x is negative, which I'll look at there, so I'm going to erase that positive sign and say there's the final answer, a negative radical 15 over 4. This can be for some students. I've been around long enough where this can be heavy for some students. And some students come to me with lots of experience, and they may have had the course before, and so they sort of recognize this more quickly than some who've never experienced this. So I've got to be very careful how I approach this. So guys, that one's out of the way. This was cosecant. We come back and put it in. It's negative radical 15 over 4. Now, tangent. Now, if I can find tan, I'll run find tan. Guys, does anyone have an idea of how to use an identity to support your answer and define tangent? I'm hearing, I think, what was it?
Sine over cosine.
Sine over cosine, love it. Here we go. Tan theta can be expressed as sine over cosine. And she's telling me, Professor, you've already discovered sine is negative 1/4, so I'm going to put that right there. Over cosine. Cosine's that strange negative radical 15 over 4. And yes, the 4's will cancel. If you rationalize this, it will be a positive answer. You're going to end up with a radical 15 over 15. Well, a nice problem to open up class and remind you what we were doing yesterday. Secant. Which identity, which property could I use to maybe express secant? In fact, I think I have that one written as what? 1 over cosine. And we've already discovered what cosine is. It's right here. So it says 1 over that, which merely says do what? Flip this over, form the reciprocal, and you'll find secant, which is going to be now negative flipped over 4 over radical 15. Rationalize, negative 4 radical 15 over 15. Another answer. I should put on the side here, yes, secant. And what I was looking at to justify this is 1 over cosine. Cotangent? Well, I think I mentioned something about cotangent. Here it is. Cotangent could be expressed as cosine over sine. And if it is, I found cosine earlier to be this. Over sine to be this. Will be a positive answer. The 4's cancel out, guys. Looks like if there's no mistake, it's radical 15. And as I said earlier, Justification, I use cotangent is equal to cosine over sine. And we're done. Just finding missing parts by using those identities. That's all we're doing. Mr. Park, do me a favor for us to take questions. Just a quick favor. We know the angle they're talking about, theta, is in quadrant 3. I know quadrant 3, you know quadrant 3. You're caught between what? 180 and 270. You're caught between 180 and 270 on a sheet of graphing paper if you're in quadrant 3. Could you please, they gave me this, where was it? Let's go ahead and change it to sine. Do it this way. Find inverse sine for me of a -1/4. He's going to do an inverse on this. You guys don't have to worry about it. He's going to just do a little check here. And I'll tell you later in chapter 6, I think it is.
-1/4, right?
Yeah. Inverse sine of -1/4. See what it gives you.
-14.47.
Okay, they're giving it for a reason. That's exactly right. Right, now take 180 plus that 14. We'll place it where it should be placed.
165.
Close to 165 degrees is the angle they're talking about. 165 degrees approximately. Now, am I worried about finding the size of the angle? No. No, I'm just asking you to find the values and a justification. Jonathan, what was that question?
In the book, it was like, so sine theta equals -1/4, and they were like, that is y over r.
That's in chapter 6.
Okay.
We're doing it for chapter 5 with the unit circle right now. You're into probably a right triangle maybe. Or they introduce the
They
R.
already
I know they do.
introduced it.
They do introduce the R.
But it still works out.
It does.
I got a little like, oh my gosh.
It does,
But
it
still
does.
works out.
Absolutely, still works out. And by the way, if your radius is 1, if they put y over r, you put y over 1, you're about right back to where we are. So if that r, which means radius, and
Yeah.
I'm doing a radius of 1, I'm talking about the unit circle. So y over 1, we're right back to where we should be. Absolutely. Guys, any questions here? But you cannot do one of these on the quiz next Wednesday, and certainly on the exam on Friday of next week, which just, I think it's all tree for the test, unless you know these. And you've got to justify it with one of those properties. Now, with all that said, that's part 2. Had to do that. Part 3, I said, Professor, what else is in chapter 5 here? I thought also about this. I go, hold on. I had better do this, even though it's going to take a little effort to do this. But I think it's going to help us. Guys, we're going to construct a table. And do something with it. See if you guys sort of make a connection here that may help us. And looks like I have to look at is to look at, and also divide this up into, I did this. You guys might help me fill this table in, but first to the table. Mr. Professor, what are you going to do here? I'm going to go through, now this is nice. Try to make a connection for you. I have this so I can talk about quadrant 1, quadrant 2, I wish the textbook had done this, quadrant 3, quadrant 4. 4 quadrants. Right above each one, I'm going to identify the coordinates as either being positive or negative, which is going to play a part. So guys, quadrant 1, we know a point in quadrant 1, coordinates are both positive. Quadrant 2, negative, positive. 3, the coordinates on a sheet of graphing paper, both negative. 4, positive, negative. Just going to set a little table up for you. Now, did I yesterday work with a 30-degree angle, and we dropped a perpendicular, I came up with a 30-60 right triangle relationship. Did I also get a chance to do a 45? Did we discuss the 45? Pi over 4. I did not discuss the 60. Okay, so I'm going to include the 60 in the table and give you the values here. I did not actually derive it for 60, but I did the others. And what I want to do, if I'm careful, is to do this. Quadrant 1, I want to look at, yes, pi over 6. That's 30 degrees. Pi over 4 and pi over 3. Those are the major ones. Those are really, really major ones you can deal with without a calculator. What I also did, and watch carefully here, I then took pi over 6 into quadrant 2, into quadrant 3, into quadrant 4 to see what effect it has when it's moved into those quadrants. So guys, can you help me out here? Let me just translate what I want. I'm moving pi over 6, 30 degrees, I think I did this yesterday, into quadrant 2. Now what angle over in quadrant 2 is related to pi over 6? Does anyone have an idea? Say it again.
5 over 6.
5 pi over 6. Hang on. 5 pi over 6. You guys who like degrees, you can convert that real quickly into 150 degrees. Now please tell me, why did he choose 150 degrees? I put it in radians. What relationship does 150 have with 30? Why am I aligning this up with that pi over 6? He says 150 in quadrant 2, professor. And if I do a quick sketch, guys, that's what it's all about. This angle's over here. I'm in quadrant 2, and it's 150 degrees. Let me use degrees. Now, where's the 30 I'm relating it to? Where's the relationship? Is there a 30-degree angle here? Caroline?
No, 180 minus 30.
Right there, the little angle in the corner, along the x-axis, is 30 degrees. 150 plus 30 makes 180. So this little angle right here is 150's reference. They call it a reference angle. So this will tell me something about 150, or 5 pi over 6. Beautiful. Now, before I fill in the next quadrant 3, let me move it. Caroline, thank you. Let me move it now down to quadrant 3. And guys, now the angle looks like this. Bear with me, please. That's in quadrant 3. Now what size angle do you think that is, where I'm still focusing on 30? Thank you, 210 degrees. It's 30 over 180. That pushes me down into quadrant 3. So it's 210 degrees. Now I prefer radians today. Does anyone know what 210 looks like in radians right quickly?
7 pi over 6.
Love it. Finally, quadrant 4. Let's see what effect I have in quadrant 4. If I go to quadrant 4 and I move it into quadrant 4, see the relationship? All the way over here. Looks like this. Now what does that have to do with 30 and what size angle is that? I'll place 30 right here in the corner for you if you wish. This in the corner has to be 30. 330. 330 degrees. 330 converted to radians. You can use a conversion factor. Help me out. What is it?
11 pi over 6.
There we go.
11 pi over
11 pi over 6. Now each one of these are connected with pi over 6. Watch what's going to happen here shortly. Watch what's going to happen. And by the way, since I'm looking at pi over 6 first, does anyone recall the ordered pair after I dropped that perpendicular and went through a 30-60 right triangle? What ordered pair did I have on that unit circle that corresponded with pi over 6 or 30 degrees?
radical 3 over 2, comma 1/2.
Look at that. Some of my colleagues are telling me their classes are, I said, how's your classes doing? How's yours, Ramsey? Oh, I love it. I love it. What's wrong? My students just sit there, they don't talk, they don't say anything. I ask them questions, no answers. Not here. Now, here we go. Let's try it for pi over 4. You gotta do the same thing. Now guys, can't do it all as well as I did this one. But we gotta look at now pi over 4, taking into those quadrants. That's 45 degrees. Anyone tell me, as I move into quadrant 2, something like I did for 30, as I move into quadrant 2, 45 degrees, what size might that angle become? 3 pi over 4, which is 135 degrees. So I need 3 pi over 4, right here. Now, let's take 45 degrees and take it into quadrant 3, like I did the 30 earlier. Now what size angle am I talking about with the 45? Yeah, exactly. 180 plus 45 is 225. In radians, that's 5 pi over 4. And finally, in the quadrant 4, guys, it will become 7 pi over 4. They all have a connection with pi over 4. Now, what connection is it? Well, first I need the ordered pair. And I think I did this also yesterday, guys. I think the ordered pair was, if I'm not mistaken, for a 45-45 right triangle. I think, was it root 2 over 2? Root 2 over 2. I'm so glad I thought about this. Placing these on a table for you, but I want to start making some connections here. Now 60 I did not do. I did not drop a perpendicular for 60 and go through all the work for 60. I'm going to tell you what the ordered pair is though. You can find it yourself. It's merely this one. In other words, the one for 30 just turned around. That's one for 60 degrees, or pi over 3. That's the one I did not do, but you could easily do it with a triangle and find those. Miriam, help me out. I need to take that 60 like I did the 30 earlier, take that 60 into quadrant 2. If I move 60 into quadrant 2 and I work with it like I did the 30, that would be 180 subtract 60, which becomes 120. Now what's 120 look like in radian measure?
2 pi over 3.
Beautiful, 2 pi over 3. If I move that 45 degree angle into quadrant 3, Philip, that's like 180 plus that. 180 plus 45 is what, 225? What's 225 look like in radians? Oh, whoa, I'm 45. No, this, that's too fast here. We got pi over 3, 60. 60 down into quadrant 3 would be what, 180 plus 60. That's 240. And what's 240 look like in radians?
4 pi over 3.
I heard 4 pi over 3. Finally, if I do the same thing with not 45 but 60, move 60 finally into quadrant 4 like I did the 30 earlier. That's like 360 subtract 60 is what, 300? And 300 looks like what in radians?
5 pi.
5 pi over 3. There's your tree course. There's the tree course. Big chunk of it. You just remember the numbers here, the quadrants and so forth and so on. Now, on the side here, you said, Professor, how can I use all this? I sort of follow how you got those numbers. How can I use this? Okay, on the side here, like your quiz next Wednesday and your exam next Friday. If you're asked to find this, sine of 5 pi over 6, where sine is y. So guys, if we look out here, is 5 pi over 6 one of those in the table in the green there? I think 5 pi over 6 was right here. Now looking for the sign. Sign should be what? Y. Y should be positive. So the answer is positive. Now what is it? It's positive what? 1/2. Done. Finished. If I ask you for a cosine, let's try 5 pi over 6 again. I know and you know it's x. Thank goodness 5 pi over 6 is in that table. If there it is again, cosine looking at the x, well, the x must be negative, so the answer must be negative. Negative what? Well, on the side here it says the x is radical 3 over 2. So it's a negative radical 3 over 2 as I match these things up. That's how the table's going to benefit me. Let's see if I threw anything maybe a little bit more demanding, not too demanding. Tan. Let's put a tangent. Guys, in this case, we're going to do tan of 5 pi over 3. Ah, right there it is. 5 pi over 3. And I know tan's definition is y over x. Guys, I'm in, right here at 5 pi over 3. Look right above. Right there it is. So if I place y over x, I'm placing a negative over a positive. I've been quadrant 4. It's going to give me a negative answer. And if I place y over x, hang on, right here, those are the coordinates. So I'm placing radical 3 over 2, that's the y, over, looks like for 5 pi over 3, guys, was it 1/2 for the x? Clean this up, 2's cancel. Please tell me, does it merely give me that? Is this table sort of making sense as we go through it? Little connections. Okay, next. Cosecant. I did this one, 11 pi over 6. Back to 11 pi over 6, we're back up here. 11 pi over 6 is right here. Cosecant, by definition, is 1 over y. And here the y is negative, so I know the answer is negative. And if I place 1 over the y, what y are we talking about? The 1/2. Just a little reference back there. Guys, check and see if I did that correctly. I did it quickly. Is it negative 2? Is it negative 2? Connections, connections, connections. That's all we have. Just connections. Now, let me see if I'm ready. Oh, I am ready. Who would like to be excused from the quiz? Oh, yeah. I'd like to. Yeah, right.
Where'd you get that negative? I haven't even gone to that. I'm like way behind. Where'd you get that negative from the cosine?
For cosecant.
No, on the left
Oh,
side.
look here.
The green.
Oh, green.
Left of you.
Okay, what
The negative square root of 15 over 4.
Oh.
Where'd that negative come from?
Hang on a second. I gotta find it. The negative.
To the left.
To the, where your finger is to the left? Yeah.
And
You're right. Yeah, right.
over there.
No.
Further.
That's what, tell me again. I didn't understand what you said.
Negative square root of 15 over 4.
The previous problem.
Oh, you're going way back here on the
Yeah.
previous. Oh, my goodness. Okay. Negative radical 15 over 4. This one.
Mm-hmm.
Okay. That was asking if I did a square root. So the square root of 15 over 16 is like radical 15 over 4. I can't do anything with 15. That's how I got that radical 15 over 4.
So it's just negative, it's not plus and minus?
Beautiful. Now, y is cosine, and where was this? We're in quadrant what? 3? And cosine is x. By definition, the x coordinate is negative. That's how I got the negative. And now I see what you're asking about. That's why I attached that negative sign. Yeah, I thought you were talking about this over here. So far, so good? Now, like I said though, now who would like to be excused? Even though it wouldn't be nice to just get up and leave when the quiz starts and just turn around and smile to the class and just, good luck class, and leave. Miriam, wouldn't that be nice? Caroline? Of course, it'd be super nice. Now we'll see what might happen here. Number 5. Looks like this. Sine of 14 pi over 3. Nice. When I did this planning for you, I even wrote the word nice down. It's so nice. Now you go to the table and say, Francie, I follow you so well today. You got everything organized for us on a table. This is beautiful. This is great. 14 pi over 3. Whoa, I don't see it. Oh, hold on. I don't see it. This is another little extra credit to be dismissed from the quiz. No. 14 pi over 3. Miriam, I don't see it. Now, there's different ways to think about it. Maybe I can do something to it that will take me back to that table. Maybe. But right now, 14 pi over 3 is not in the table. But yet they're asking for, or I'm asking for, what's the sign of it? Well, you say, Professor, a little, few points I can gain. At least I'll put a Y. I'll give you maybe a half a point for credit there. You know what the sign is Y. This is the way I'm going to approach it. You guys may want to approach it a little differently. Ben, you got a question?
I was just going to give you a method to.
Oh, beautiful, beautiful. Let me hear your method.
Can you subtract 2 pi from 14 pi over 3 and then try to solve it?
Whoa, so you made, okay, the full circle is 2 pi.
Yeah.
And you want to subtract 14 pi over 3 from that.
And then you turn into sine.
Now, will that take me back to one of those in the green in my chart?
Yeah. And go, or it turns sine, it would turn into sine 6 pi over 3. And then it turns into like sine.
That's why I like this class. I think it's going to work. I think when I show you what I had in mind, I think you and I are thinking along the same lines here. I think it's going to work. I'm going to do it this way. You guys may have a little different technique here. I say, well, Professor, what if it's not in the table? Then I've got an issue. To resolve that issue, I'm going to do this. Are you kidding? It's a fraction. Go ahead and divide. Divide it out. I think we'll get very close to what Ben's saying here. Guys, if I divide this out, I think this goes, help me out, 4 times? That's 12 pi across the street in the middle school with a remainder of 2 pi. Yes or no? So that means this can be expressed as, here we go guys, 4 pi plus, put it up here, 2 pi over 3. 14 pi over 3, if I made no mistake, is the same as in fractions back in elementary school. It looks like this. Is that true? Now, you gotta be careful. 4 pi means you're gonna make 2 complete revolutions. So let me make a sketch to illustrate what this looks like. 4 pi, everyone knows, 1 complete revolution, I left a little space there. 1 complete revolution is 2 pi. Now I want 4 pi. And we'll make another complete revolution. There's 4 pi. Then Philip, I can't stop there. It says, no, don't stop there. You took care of the 4 pi, Professor. Illustrated. But now you need to move an additional 2 pi over 3. Is it true? Now where is that additional 2 pi over 3, if you like to think of it as what, 120? Where's that going to take you? Into quadrant 2, beyond 90. So that angle is going to finally land in quadrant 2. By the way, as soon as I saw that 2 pi over 3 come up, did that really take me back to that table? Is it now in that table? 2 pi over 3? Let's check to see if it is. Was 2 pi over 3 mentioned here somewhere? Oh, there it is. Obviously, it took me back to the table. I'm looking for sine, so I guess sine is y, so maybe the y is radical of 3 over 2? After all that effort? Yes or no? Took me back to the table. Adrian, if it doesn't take you back to the table, you're in trouble. If I give you something where it's not going to take you back to the table, we're going to call Mr. Park. He uses graphing device or whatever he uses over there. Use coding also, don't you code? Yeah, he does it all. You have to call upon him. But do me a favor, Mr. Park, before I leave this one. Would you just do your business over there? Put your, make sure it's in radians, radian mode. Find sine of, just put it into radians, sine of 14 pi over 3.
It says 0.
Sine of 14 pi over 3, what was it?
Root 3 over 2.
It is root 3 over 2.
Uh-huh.
That's what we have. Anybody think nice? You see some other things, say, whoa, Professor, you've never, 1,000 pi? Maybe it'll take you back to that table somehow, or something that you recognize, we're good, this one did. Now let's try one more here, number 6. The table would be very helpful. I brought in this one, next. I'd like to find, why not, the tangent of 23 pi over 4. Which is not one of those green listings in the table. So my method, Ben, were you sort of thinking the same thing I just did?
Yeah.
Okay, I thought so.
I was just saying you can keep subtracting.
You said subtract from 2 pi.
You can just keep subtracting.
I got you.
2 pi.
Oh, beautiful. Absolutely. Absolutely. I now understand what you're going to do here. Yeah, I used the 4 pi there. Absolutely would work. Okay, let's divide this out, guys. We'll do it this way. Divide 4 into this, like a fraction. I think it goes 5 here. 20 pi. It's like a remainder of pi over 4 if I have everything correct. If you rewrite it as this, 3 pi for remainder. And we got 3 pi over 4. Straighten this up. We step back and look at it, guys. You agree with this? Is this another name for 23 pi over 4? Now, I'm gonna locate it. By the way, I do see, okay, we'll see. Here we go. I see a 3 pi over 4 coming out, but if I want to locate it, just to play it safe here, Mr. Parker will check this for me. 5 pi, guys. There's 2 pi. We'll try to locate it. And I showed 5 pi. So let's pick up from here, do another complete revolution. That's 4 pi. I want 5 pi. That means I need to move not a complete rotation, but what, half? Over to pi from here. There's 5 pi. Illustrate. And then we'll stop there. From there, Jonathan, we'll drop down 3 pi over 4. Now, if degrees may help, that's 135 degrees. That you got to pick up from where the red stopped and move an additional 135 degrees. That's going to take me into quadrant 4. Is that true? There's a location by finding out, at least know the location. I'm in quadrant 4. And just out of curiosity, if I'm in quadrant 4, we all know what this is. Those are the coordinates. Now, I'm concerned about, I see 3 pi over 4. Guys, was 3 pi over 4 over here in the table? I see 3 pi over 4 here. I'm looking for tangent, which says we're what? Y over x? Maybe. Mr. Parker's going to check it for me. And it looks like y over x here for that would be, hang on, 3 pi over 4 right here. Would be radical 2 over 2 over radical 2 over 2, I think. Now, you know, and I know that's 1.
1 looks negative.
Yeah, hang on. Exactly. Looks like, but at least that much is 1. Is that true? Now, which quadrant did this thing finally land? Quadrant 4. I'm going y over x. If I place y over x, am I placing a negative over a positive? If I'm in quadrant 4. We said the angle is in quadrant 4. So should I prefix this with a negative, as I'm hearing? So professor, not just one, but its location says it should be -1. Mr. Park, did you check this one out for me? Find tan of 23 pi over 4. And see if it's -1.
-1.
Isn't that cute? That's cute. Number 7. Adrian, will help me out with this one. Adrian, I brought this one in. Looks like I have your name written right next to it. Ask Adrian. When? I'd like to find the exact value for this with your help. Secant 19 pi.
Well, 2 pi can go into 19 pi about 9 times, which leaves you with just 1 pi, which is 180 degrees, and then secant is just 1 over cosine, which is 1 over -1, which is -1.
Oh, other instructors would like to hear that. I love that, the way you describe this. And by the way, you know, 19 pi is not in that table, but he's telling me, he said, Professor, if I want to sketch and find where it is, I could do this, like you did the others. Guys, here goes. 1 revolution, of course, that's 2 pi. If I do another revolution, I get 4 pi. Miriam,
Yeah.
I want 19 pi.
And on to
If I do another revolution, that takes me up to 6. I'm not gonna draw all these. And it continues like that. Now, Adrian, he says, Professor, just go ahead and divide this by 2 pi. Each revolution is worth 2 pi. And see how many complete revolutions you would have to travel. I think he's telling me that. Is that true? Is that what you're thinking? Pi's, of course, will cancel. So it's merely just 2 into what, 19?
Yeah.
What was that, 9.5, I guess? 2 into 19? So what does that tell me? You're gonna make what, 9 complete revolutions, is that true? And then half of another. So guys, 9 complete revolutions, each 2 pi, that's 18 pi. And then you're gonna eventually stop, let's say this is last one, you're gonna eventually stop there. 9 complete revolutions, then half more. So you're gonna stop here, and I think this is right on the circle at what, -1, 0? After all that business, I want secant. Secant's definition is 1 over x, and you're telling me it's 1 over a -1, Adrian? In fact, it's -1?
Yeah.
And I like the way you expressed it. He said 1 over cosine. Absolutely. That's done. See all these connections between the trig functions? Absolutely. Okay, let's try one more here that I gotta watch. So, let's chapter 5 done tonight, which I will. Oh, it's good, good, good. Here we go. Last one, number 7. Looks like I'm trying another, we'll try tan. And this one guy says find the tan of 5 pi over 2. Not in the table. I like to locate it. Now, if you want to go through and divide this out like I've been doing mine here, you may have another system here. And the thing is what, 2 pi? 4 pi, remainder of pi, right? This is plus pi over 2. That's another way to express 5 pi over 2. Is that true? So it says if you want to illustrate that, after you do that division, Let's move 2 pi, well, that's easily done, this is one complete revolution. And from there, move an additional 90 degrees, pi over 2, you're going to land there. Ordered pair, 0, 1. You're right on the y-axis. I'm asking for tangent. Tangent's definition is y over x. We'll use that definition. And guys, if I place y over x, I'm placing 1 over 0. Which tells me what's happening. There's no answer. It's undefined. Farbon, if I see you later on in campus after you finish this class, and you see me walking across campus, maybe some point in my class, I'm gonna find you. I'm gonna ask you what's the tan or 5, 5, or 2. You say, Professor, I'm going to lunch. I've got a class later on. What? What's the tan of 5, 5, or 2 for our lunch? He's gonna say, I hope he says undefined. There's no answer. So these will give me an undefined result. Now that took me, took me an hour. A little recap, a little connection. I'm trying to get this chapter 5 finished up. But I thought, guys, I think this right here, I think this is going to help. Big time. You can get back to this table somehow. This table's beautiful. Sometimes you cannot get back to that table. So it may be one of these that's right on the circle, like this one right here, this one over here. You know, right on the circle, did not fall in that table there. It still can be done though. Now let's see what I said here. Oh, nice, 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 nice. Now I'm to the last part of chapter 5. Can't believe it. I'm down to the last part of chapter 5. But it's going to take some time. Now, after you look at all this, now I'm going to ask you, please close down chapter 5. Make sure your students know before they move into a calc course the graphs of these trig functions. What does sine as a function look like? I know its definition. Sine is y. Cosine is x. But what do they look like if I went to a sheet of graphing paper and graph them? What does a graph look like? Parabola? No. Straight line? No. So I need to know what that parent graph for a sine looks like. Absolutely. Jonathan, before I jump into it, I hate to change gears here, but he was asking yesterday about a particular problem that may show up on let's say the exam Friday. So he's one that does his homework. He says, Professor, I saw one in the homework, I tried it, and he says, finally got some help.
Yes.
He finally got some help there, and he says he's discovered then how to do it. And I gotta show the class what it was. I placed it on the handout I'll give you guys today. I thought about it when I was creating the worksheet last night. I actually placed it on there so you guys can see the one he was concerned about, and we'll work it out here shortly. But before I do that, how's all that look? If I were you, and I was seated where you are, and one time I was, and my professor walked in, and all of a sudden I had some good professors, solid professors. And I've always told you guys, when I went to grad school, the women professors were much stronger teachers. Much stronger. The men knew the math, but they were in a rush to get back to the office and do the research. They were not that concerned about us in class. They rushed back to their office, closed the office door, and started doing research. That's all they were into. The women professors I had, more understanding, held discussion sessions like I sort of do at 2 o'clock. They had held discussion sessions. Yeah, those male professors, no way. They were in their office doing research. Okay, so there's much more to teaching than just research. Okay, guys, I'm gonna erase this. The little time I have here before we take a break, I want to do this. also I need to give Park Arena a little time to tell you guys about this extra credit. And when they want it turned in, I'll get that extra credit to you today. Guys, let's jump into, see where I left off down here. Let's go ahead and call this part one as it's starting over. I like to sketch this. F of x. I notice your textbook writes this as sine x. I like to think of myself as sine x. Okay, I want to see what that looks like as a graph. Definition is y. We know the definition, there's no problem with the definition. But what does it translate into, Professor, if I see it in a picture form, a graph? Now what I'm gonna do, see what the parent graph may look like. I'm gonna go back to right quickly the unit circle. And just a few points to look at and do this. And we'll start with 0, point out the ordered pair was this. We saw this before. Pi over 2, ordered pair was this. Here was pi, ordered pair was that. And 3 pi over 2, ordered pair was this. And finally, one complete revolution takes me back to 2 pi, so I could call this also 2 pi. Major numbers to work with, ordered pairs. I think we did this earlier, the ordered pairs. Now, what I'd like to do is now, I call it unwrap that unit circle. And when I say unwrap it, take it to a grid, and see what's going to happen here. So, first thing, when I say unwrap this, I'm going to first pick out, choose my angles, 0, pi over 2, pi, 3 pi over 2, 2 pi. I'm going to place those like critical numbers on my x-axis, like this. The numbers, I see 0, 1, I'm gonna mark that like this. I see the max is 1 for the y coordinates, and maybe a minimum of -1 here. As I examine those ordered pairs. Now I'd like to go through and start plotting points. My first point, let's see what's going to happen here. Guys, if I'm looking at the y, and I am, that's what sine is y, but the first y coordinate is 0. So that means at the beginning, your graph's going to start at 0. When I reach pi over 2 up here, and I'm looking at the y's here, that's what sine is, it's 1, the y coordinate. That means that pi over 2, I'm up here, from that unit circle. At pi, the y coordinate is 0. I'm back on the x-axis. 3 pi over 2, I'm down here, it's -1 for the y coordinate. And 2 pi, and back to one complete revolution, back to 0. And those are my y coordinates plotted. Directly from the unit circle. Connect, they will connect something like this. Quick shape. Something like that. And that is one cycle of the graph of the sine function. One cycle. Now, suppose I pick up, though, Jonathan, after 2 pi and do it again. I could go higher. So it says, well, if you want to do it again, you could draw another cycle that might look like this. And can I draw another cycle from there if I wish? So how many cycles could I draw of this graph? Infinite. Now, which one do I want you to know as your parent graph? Because we're going to start doing some transformations on this. The parent graph, I'm going to accept as the blue one. From 0 out to 2 pi. Now, let me share with you a short story about this. I had a student, and since the middle school is right across the street, I was teaching this class at 5 o'clock on Mondays and Wednesdays. And I had a kid from the middle school, I think he was in 7th grade. And those teachers across the street told me, said, we've done Ramsey everything we can with him, he's out there. We've held sessions with him, he knows algebra, he knows algebra 2, he knows geometry. We can't challenge him much more here. So we're gonna send him over to SMC. And he did. I was lucky enough, because of the time schedule, my class started at 5, so that's the time that he got out of middle school. So he walked over, I didn't know him. And like I did the first day for you guys, I sat down with my roster, called your names, you came up, and I called his name, and it was a child. A child. I thought, oh, he must have us, he's at the wrong place. He must think he's supposed to be over there. And I looked at my roster, but his name's on my roster. So I welcomed him, gave him a copy of the syllabus, and I thought, whoa, okay. 7th grade. So he came over, sat in class, and he's one of those that watched everything. Everything that I did, he watched and he listened. But did not speak. Did not ask one question throughout the entire course. Did not take one note. Just sat there and watched. Watched and listened. That's all he did. When class was over for our body, he just got up, left, and that was it. So I thought, oh no, this kid, I don't know, he's too quiet. He may be sitting there doing nothing. And maybe, I've had students do that before. They'll just sit there and do nothing, and all of a sudden on the test they do nothing, and therefore they're gone. I thought, he must be one of those. He just looks like he's not participating, he just sits. Boy, was I surprised. Was I ever surprised? First exam came up. Started scoring the exams, 7th grader, perfect score. Perfect score. I thought, whoa, well, maybe he recalls some of this from over there. Got to exam 2, you know, these exams get a little harder. Exam 2, still no word. I thought, nah, he's gonna mess up. He's gonna mess up. He's not asking any questions in class. He's alert, but he's not asking anything. Very quiet. Exam 2, scored the papers. He was number 1, perfect score. Exam 3, are you kidding? Perfect score. 7th grade. Exam 4, I think I get 4 exams. I think I told the same story to you guys when you were in my class. Perfect score. I thought, wow, that kid is accelerated to be 7th grade. 7th grade, I don't know how old he was, 14? I don't know, he was 14 years, I don't know. I thought, wow. So, I thought, wait now. I'm gonna challenge this kid. But how am I gonna do it and not challenge the class altogether? So I thought, well, I'll place something on the final exam, like a little extra credit, that's really, really tough. I mean, I've forgotten exactly what the problem was, but I created a problem. Ooh, it was tough. But it was extra credit. I was going to see who could get the extra credit. I was anxious to score this. I thought, oh, he's gonna finally make a mistake. finals, Miriam, start scoring. The reason I brought this up, the extra credit concerns something about this, a graph that I had to do. And I asked him to draw a cycle of a graph for me. You guys already told me this thing has infinite cycles, Professor. I asked him to, for the extra credit, to draw a cycle. I didn't tell him which one. But most students who tried the extra credit, for example, I think most students in class, I would draw this one. That's the parent graph. That's the cycle out. That's the easiest one to work with, is that blue one there. That's the parent graph. Just draw that cycle. So the question asked Michael for a cycle. I could not believe. So I started to score the papers and I thought, oh, he missed it. I started scoring the papers. He missed it. How about that kid? Us, me included. I would draw this. Oh no. He drew the cycle down here. Because those cycles, it continues forever. They call it a sine wave. It continues forever. For what reason in his mind? He drew it down here, so I thought on my key there when I was scoring papers, I was looking for maybe something like this. I said, oh, he missed it. He finally missed something in class. I said, that's unusual. So I got it wrong. And I started thinking, oh, let me go back and take a look again. My directions, draw a cycle. He drew that wave down here, Miriam, and he had it labeled perfectly down here. He got the credit. Now, he finished up. He didn't say a word in class. Not a word. Not a word. Just watched and listened. That's all he did. They had all those perfect, all these students I've ever known who had perfects on all the exams and got a perfect, I thought he messed up, a perfect on the final exam. And like you guys, I like talking to you. We talk. I had a discussion session. He didn't attend that discussion session. He never attended the discussion session at 2 o'clock or whatever time it was. Oh, he didn't do that. Nothing. He was just out there. So I really didn't get to know him. I would go up and try to talk to him. And, you know, he would just shake his head and yes, 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 or no. Do you understand? I asked him, do you understand? Boy, did he ever understand? I said, you understand? Oh, yes, sir, I understand. Where that kid is these days, I don't know. I don't know where it's Elon Musk, maybe. Maybe I'll tell Elon Musk. Who knows? Who knows? I don't know where that kid is now. I'd love to know. No contact. Some students will email me later on when they go off. They'll say, Professor, I'm doing well. I'm at the university now. I'm doing well. And we communicate. Like Arena and I will communicate. Mr. Park, when he finally leaves, we'll communicate. They'll send me an email, let me know how they're doing. Many students email me. I get emails almost daily from somebody out there. Let me know what they're doing. This kid, I don't know where he is. But he did it. Now, that was very unusual. Very unusual to have a student get all perfect scores and not ask one question. And return the paper to him. If I got perfect on my exam, I'd at least smile. That's all nothing. He just said thank you and took the exam. That was it. That was it. So guys, with that said, if I say draw a cycle, please. I have a lot of papers to score. If I say draw a cycle, I'm hoping, maybe I should be more specific on which cycle I want. But if I just say draw a cycle, I think most students would draw this, and I'd go way down here and draw the cycle. And the thing was, he had it labeled correctly down here with the correct numbers down there also. So he knew what a cycle was, but he just did not want to draw that cycle. We're going to accept this as my parent graph. To close this down though, guys, if I do this, I'll set this as a SketchUp sine wave of this function. for the domain, I'm asking for this. What will I accept for the domain on this function? The x. Well, if I look at the graph and have the graph done, does it go forever? So exactly, all real numbers. Negative infinity to a positive infinity. Now the range, a little different. The up and down, no matter what cycle you look at, the lowest it drops down to is -1. And the highest it goes up to 1. Now look at the clock up there. You know and I know what's going to happen. I'll accept this as my parent graph. This is my so-called sine wave, what the sine function looks like. We have to do this. Eventually. Aren't we going to have fun? And how are we going to do these? Transformations. Now, has Ramsey come up with another way to do it much quicker? Yes. I'm not going to show it to you till we do at least a couple of these through transformations. Hey guys, on this one, if I were to do it right now at this point, every student in class would say this is a vertical stretch. So professor, you got to go back and take this blue parent graph and stretch it vertically by a factor of 3. And you'll show that, like we will show transformations on the quiz tonight. And then this might mean horizontal shift to the right, how much? Pi over 2. That's a little different for us, but that's what it means to do. A horizontal shift to the right, pi over 2. And finally, vertically shift the graph up 4. Then after you do all those transformations, the rest for the domain, the range on that final result, after you do those transformations. That's the issue, to do this. Now, how many trig functions do I have altogether? 6. How many graphs do you see on the board right now? 1. To close down chapter 5, I'm supposed to show you all 6. That's why I brought a handout here, with those, all 6 on them. I'll give to you. I'm supposed to show you what all 6 trig functions look like as a graph. I've got sine out of the way. I've got 10 minutes before the break comes up. I'm going to do one more cosine. I'd like to know now what's the, oh God. For this class, I just changed my mind. Miriam? Oh, yes, I've been bragging to you guys and I'm going to see. Just thought about it. Usually I do cosine. Park and Arena, when I had them, I think I did cosine. After I did sine, I probably did cosine, the graph, and tangent. Not for this class. This is going to take me to the break. I want to graph this. Okay, guys, this is my parent graph here. Now let's sketch. Watch what will happen. Y is equal to cosecant. I'd like to know what the cosecant graph looks like. Anyone have an idea? What you might approach first? What your thinking might be before you jump to the grid and start graphing? Far about it. There's asymptotes. Then you're going to, let's see, your graph tonight, you're doing a transformation, you know, well, you have asymptotes on your rational function tonight. We got asymptotes on this. Well, why not? That's something else. It will contain some asymptotes, absolutely.
Cosecant is equal to 1 over sine.
Who tell me again?
Cosecant is equal to 1 over sine.
Hey, hang on. Hmm. 100% correct. Now, do I have the sine graph already done? Yes. That's why I changed my mind here. I've already done the sine graph. Ben, that was you, wasn't it? Yeah, he said, Professor, cosecant is 1 over sine. If he says 1 over sine, guys, in essence, he's saying The graph you're looking for is the reciprocal of the one you have up there. So if I know what reciprocal means, I can go to the blue graph, which is the parent graph for sine, do a reciprocal, and if I got room here, if you do this, I hope I do, just for a rough sketch, let's see what, erase this, let's do it quickly. The blue one is one cycle of the sine graph. Now, let's do a reciprocal. And that's exactly what Brian just told me. That's the relationship between these two. Okay, so here goes. Nice. My first point is at 0. Be careful now. What's the reciprocal of 0? I've been bragging on you.
No solution.
No, that does not exist. If I say, what's the reciprocal? You flip something over, form a reciprocal. If I say 0 and you flip it over, you get 1 over 0. Don't you? And that's undefined. So I'm going to start out with, Barbara, I heard what you said. I'm going to start out with, to show it's undefined at 0, a vertical asymptote to show it's undefined. Now, Phil, by the time I reach pi over 2, my parent graph for sine, its value is 1. Now tell the class, what's the reciprocal of 1? It is 1. It does have a reciprocal. At that point, it stays where it is. At pi, I'm back at 0 on this parent blue graph. And I'm looking for the reciprocal. There is no reciprocal there, just like there was none for 0, so there's another asymptote. 3 pi over 2, staring at me. I see -1 is the value of 3 pi over 2. Guys, if you think about -1, I'm doing not an opposite, but I'm doing a reciprocal. What are you going to get? Is it -1 itself? -1, flipped over, form that. -1. Finally, I reach 2 pi, which is right back at 0, which we've already said does not have a reciprocal, another asymptote. Now, I'm so glad I did this for the break. We have asymptotes. You're going to have asymptotes in just a few minutes on that quiz. I need to know what's happening, I'll graph it in red, with this graph. And the graph's going to be cosecant. I see someone motioning for me here. I got to pick up this point, and I got to follow those asymptotes. So I don't have much choice. Better here, so I can see it. Might I have a branch that does something like that? Which is strange as you know what, but that is where it belongs. In between these two asymptotes, well, I got a point to work with, down at -1, but might get now to this, also down there. There's your parent graph for cosecant, based on the reciprocal of sine. Just took the sine graph, I had it up here on the board already for me, I'm so glad I thought of that, and now do cosecant, take its reciprocal. Go.
Sorry, maybe I didn't notice. Why did they go back up? So why did they go the opposite direction?
Tell me now, tell me again.
So wait, why did they go the opposite direction again? I think I didn't notice. Is it because of the asymptotes? Like they have to reach the asymptote.
Oh, beautiful, beautiful, then we'll follow the asymptote.
That's why.
Exactly, exactly. Does it make sense, guys? Just that quick? I did quickly. Now, before I close down, here comes the big question. Jonathan,
Yep.
if I accept the red graph as representing cosecant, that's just one cycle of the cosecant graph, this thing repeats forever. And then we'll take a break. Jonathan,
Oh.
rather than asking for the domain on that red graph, I'm going to ask you first for the range. How would you describe to someone the up and down on that red graph?
-infinity to -1.
Beautiful. Hang on just a second. Negative infinity up to a -1, including -1.
Yes.
Okay, union.
Union, including 1 to infinity.
Look at that. Perfect. Now, held up on domain. I'm gonna need a clever answer. I'll get you started. You know there are some X's that I cannot use because we have asymptotes. So I'd like for a clever student to tell me, like the middle school kid years ago did, tell me I have an asymptote at 0, I have an asymptote at pi, which I can't use. I have an asymptote at 2 pi, can't use. I gotta continue, they want the entire function. I just have one cycle. After I see 0 pi, 2 pi, what's coming up next, guys? 3 pi?
Yeah.
No.
What's coming up after 3 pi for another asymptote? Where would the next asymptote show up? Would it be 3 pi or not? And the next one would be 4 pi? 5 pi? 6 pi? Now, someone in this clever class, you gotta tell me, in your mind, create a little formula for me to show someone all of those. 0 pi, 2 pi, 3 pi, 4 pi, 1,000 pi. Guarantee you, if you go out to 1,000 pi, that's what the kid in middle school did for me. He went way out here. If I even went out to 1,000 pi, which I'm not going to, what would you expect to be happening out there? Asymptote. 99 pi, Adrian, if I have 99 pi, if I went over here, mark 99 pi, and that's going to be an asymptote. Now, can you write something up for me to show where those are located? Because I can't list all of them. It goes forever. Does anyone have anything in mind there? And I'll get you started. X cannot be. That's what you want here. X cannot be. And now I need something like, I see hands went up already. A formula. Go for it.
Is it, X times Y?
Oh, very close. And, you know, I love that. I'm gonna use n. He said x cannot be n pi, comma,
10 is an actual.
where n is what type of a number? An integer. Whoa. So n is an element of, I think I've used this in class before, z represents integers. So if you put an integer inside here, for the coefficient of pi, you're guaranteed there's an asymptote. You're guaranteed there's an asymptote. And how many integers, Nima, are there out there in the world? Infinite. So this thing would have an infinite number of asymptotes for the complete graph. Wow. I'm glad I thought about that. So we got sine and cosecant out of the way for that relationship. Guys, it's time for a break. Now, before you take a break, I'm gonna give you 40 minutes for the quiz. And this is a quiz, you know me, I'll score them tonight. And post them tonight. So when I pass this out, I don't see any nonsense.